Hello and welcome to a new problem solving session. And we have a problem from fluid mechanics at our screen, and it says Mercury under centrifuge. So let's take a look on the content of the problem. And this is a horizontal thin tube is closed at both ends. That means something. In the middle of the tube is a mercury tube of length h. You can see the air columns in both compartments are of length L, and the pressure on both sides is equal to the hydrostatic pressure of a mercury column of height h. Yeah, that's right. The tube is placed on the vertical axis, centrifuge, and set in motion. So there are two things. First, it was at the center and at rest, and then it is set into motion. That means centrifuge is set into motion. So find the displacement of the mercury filament as a function of the angular velocity omega if the temperature is constant. So Boyle's law is applicable. We need to solve this problem because we have picked up few things. One of the most important thing is the temperature is constant. We are going to use it, and we need to find out the angular velocity omega. No, the displacement of the mercury element, this thing, in terms of omega. This is our main target. So before the tube is placed in the centrifuge, or you can say the whole thin tube containing the mercury element is placed in the centrifuge, and centrifuge gets started. The pressure on both sides of the mercury tube is equal. So the forces on it are also equal. That means it is also given in this problem that the pressure on both sides of the mercury tube is equal to the hydrostatic pressure of mercury at a height h. So pressure in this case must be rho gh. Here rho is the density of mercury, and so forces acting on mercury tube from both sides are equal, and that can be simply written as PA, that is rho GHA. A is the cross section of the tube, and we also know that temperature is constant. That means Boyle's law is applicable here, and we can write any moment PV, V being the volume under consideration, and it will be a constant. So now in the second stage, this thin tube is now placed in the centrifuge and rotated at a slowly increasing speed, and I guess its displacement at some moment after the centrifuge getting started, I guess the mercury filament has been displaced by a distance x, say x, from its initial position, and the angular velocity of the centrifuge is omega, and we need to find out the forces acting on it, and I'm going to think about that the pressure must have been changed in the tube, because PV was constant and volume on the both sides of tube has been changed. This on the left side, the length of the air column is simply L plus X, and on the right side of the mercury filament, it has simply becomes L minus X. And so the pressure will change. Suppose this side pressure is P1 and this side of the tube pressure has become P2. So pressure has been changed because volume has been changed. So the forces acting on both sides of the tube on the mercury filament will be changed. And what will be this pressure P1? I'm going to use Boyle's law to find it, so that I can write initially it was simply rho G H, that is the pressure, multiplied by volume PV initially, before the centrifuge gets started. Before the thin tube was placed in the centrifuge, the pressure on the left side of mercury column, mercury filament, was this. And now it has become something like P1, this is the pressure, and volume being A, L minus X on the right side. And so that we can find out P1 will be equal to rho GHL upon L minus X. This is my equation number 1. Or you can say here that the force has become, this is the pressure, and the force has become from the right side, it has become P1A, and you can also write it as rho GHL upon L minus X multiplied by A. Simply you can write this pressure. And so if the pressure and the force acting on the other side, that is the left side, I can calculate it. And since this pressure was P2, so if I think, I can write P2 will be simply become rho GHL upon L plus X. And therefore we can write the pressure F2 from the left, that will become equal to P2A, and this is again rho GHL upon L plus X multiplied by A. So we got the pressures. So we have a kind of free body diagram that can be written here. I want to draw first the mercury column. This is something like that. Its length is L, and so if force F1 is acting from this side and F2 acting from this side. These are the pressure forces. But the mercury element performs a rotational motion, and we can say that the resultant of the pressure forces acting on the mercury filament will be equal to the centripetal force, because it's this is moving in a circle, and I'm talking about the ground frame, and that is inertial frame. But we can fix a rotating frame as well with this rotating tube, and then this force will be called simply the centrifugal force. But our main target here is to calculate the centripetal force, and that can be calculated as if the entire mass of the mercury were located at the center of the filament, and this centripetal force can be simply written as I would like to write it FC, or centripetal force, that will be equal to mass multiplied by omega square x. Omega is the velocity of the centrifuge at this moment, and x is the distance of the mercury filament from the axis of rotation, so that we can write here as so m is the mass of the mercury filament. So we need to find out the mass of the mercury filament first, and that will be density of mercury, that was rho initially, multiplied by volume, and volume will be area of cross section multiplied by its length. So this becomes mass of the mercury column, and we can multiply it with omega square x, so that we can get the centripetal force acting on it. So we can write now the equation of dynamics for the circular motion of this mercury filament, and that will be equal to F1 minus F2 equal to mass into centripetal acceleration. That means the equation of motion of this mercury filament can be written as F1 minus F2, that will be equal to m omega square x, mass into centripetal acceleration. And F1 is written here, as you can see here. F1 is simply rho GHL upon L minus x multiplied by A, and F2 is rho GHL divided by L plus x multiplied by A, and that will be equal to rho AH omega square x, that is mass into centripetal acceleration we earlier observed. And then you need to simplify this expression, and I took all the terms together and found this. This whole expression can be written like 1 minus 2gh by HL omega square minus x square by L square equal to 0. And one possible solution to this equation is x equals 0, and the other is simply, you will find it will become L multiplied by 1 minus 2gh by LH omega square. You will get this very soon. And this is x in terms of omega. If you want to analyze the result further, you can get a critical value for omega, because and it can be found from this value. The term under the radical should be non-negative, and that means it will be either greater than or equal to 0. So omega critical value you will get here for the term under radical should be equal to 0, and this value you can see here, it will become simply under root 2gh by LH. And analyze for further perturbations if you like, because my problem has been solved. Thank you very much for watching.